Any questions from last class? Anything? Or homework?
I have a homework question.
Yes.
It's for one or two tonight. Like on the open 3. That's something we should do to actually technical mass apart on something.
Okay, so this is okay. I'm going to do this kind of problem in the class today. So
Okay.
after that, you'll be able to figure it out. Anything else, guys? All right, then we are good to go on. So we have been discussing about the boundary work. So boundary work is equal to W integration state 1 to state 2 P dV. So if you know the relation between P and V, or if you can express pressure in terms of volume, then you can evaluate this integration and get your answers. And we did some of the special cases. What are the special cases we covered? Constant pressure, yes. Constant pressure. Constant volume. Good.
Isothermal ideal gas.
Isothermal process for an ideal gas. That's very important. Perfect. For an ideal gas, can we use PV equals mRT for steam?
No.
It's a big no, right? No. Right, very good. We are good to go. Now we're going to study another special case. Okay, I think I have to cover another example, right? Yes. So example 3, we'll just go through that example. Example 2. Yes, example 2. It says about a viscosity device which fills with nitrogen. And it says that it's undergoing an isothermal process, and we need to find out the work output. And I'm not going to write everything explicitly on this board. So what is the work? What is the equation that we use to work? Integral state 1 to state 2 P dV. And nitrogen, once you say it's nitrogen, it's a, what is the substance? It's an ideal gas. Very good. It's an ideal gas. So for an ideal gas, we can use this equation. PV equals mRT. Now if I lay down the data given, mass is given, which is equal to 0.25 kilograms. What is the initial pressure, P1? Everybody in class? What is the initial pressure? 130 kilopascal. Very good. Initial volume. Is it given? No, temperature is given. What is temperature? 180 degrees centigrade. And what is the final pressure? 80 kilopascal. Thank you very much. Now, I know that I can use this equation. And this is common point in the substance. Now, if I'm going to use this equation, now M, mass for a closed system. Mass for a closed system is a constant, right? M is a constant, now we know that. And R is a constant, that particular gas. And it's an isothermal process, so it's a constant, right? So we can deduce that PV equals a constant for this process. Now after we deduce that, we know what is the relation between P and V, right? So then we can use this equation, W equals volume 1 to volume 2, volume at state 1 to volume state 2, PV equals constant, so we can write C over V dV. Now we know that how to do this integration. We will end up with P1 equal times natural log of V2 over V1. We did this calculation last time, so I'm not going to go over that again. So Now one thing, what else we know? What else we know? Once you say this equation, what other equation what other relation that we can obtain?
P1, V1, natural log of V0 V1 equals P2, V2.
Equals what? P2, V2? Is that it?
Yeah. Natural log of, yeah, but it's a constant, so you can, or it's on both sides, so you can cancel out.
Right. So you can use that equation too, right? And you can use MRT1 natural log of V2 over V1 because P1 V1 is equal to MRT1, right? So we can use MRT2 also. So I don't want to confuse you over lot of equations. But one thing else. Now if I can write this also, P1 V1 equals P2 V2, right? Now what is this equal to? Very good. It's P1 over P2. Now I can substitute that equation P1 V1 times natural log of P2 over, sorry, P1 over P2. Can you see at the back? Okay. So now I have a lot of options to use. Whatever the numbers are given, I'm going to plug in these numbers into here and get the answer, right? So P1 V1, P1 V1 is not really given. P1 is given, V1 is not given. But I can use this equation. I can use MRT1 natural log of P. I'm going to use this equation because mass is given, R can be found from the table, T is given, P1 and P2 both given. Right? So I can use that equation and find P1. Any questions about that? Well, this is a lot of derivations of the same equation. Yes.
On the R, is that for the gas constant itself, or the certain gas, or the RU as the gas constant of all?
No, if you have universal gas constant, that's what you're asking, right?
Yeah.
That's RU. It is explicitly written RU. If it is R, that's for the particular gas.
Okay.
Right? So that is RU divided by A, molecular weight. So this values for certain gases can be found from table A2. If you go to table A2, it gives you R value at 300 Kelvin. So you go back to table A2 and find R, so nitrogen, M is given, T1 is given, so you can evaluate that. That's the work done during that process. Any question? So remember that we cannot use these equations for steam, okay? But still, yeah, you cannot use that equation, but you can use that equation for himself. Yes. Volume? Which state?
And he said, okay, what do we get to the
Would we need a double R because it's diatomic?
Double R?
Yeah, would we need to multiply R by 2 because it's diatomic molecules?
No.
No.
Yeah. So nitrogen is N2. So nitrogen, R value is given, that's the value. Any questions other than that? Is it okay? Is everything fine? Okay. Now, next special case is polytropic process. Polytropic process. So what is the polytropic process? The polytropic process is a process during which the relation between pressure and volume is equal to P to the power P times V to the power N equals constant. P times V to the power N equals constant. So during the process, the relationship between pressure and volume stays like that. If some process happens like this, that's called a polytropic process. Now we don't specify any substance. So it can happen, it can be a ideal gas, or it can be a steam or something like that. We don't specify any substance. Okay? Whatever the substance is, if the pressure volume relationship is like this, then it's going to be a polytropic process. Now let's look at how we calculate the work output. Okay, because now we have the relation between pressure and volume. So P is equal to C over V to the power n. Now what is the boundary work equation? W, state 1 to state 2, volume 1 to volume 2, P dV. Now if I express pressure in terms of volume, V1, V2, C over V to the power n dV. Now C is a what? C is a constant, right? C is a constant. So you can take that outside integral. Now how do you do that? It's just like this, right? Now you might be able to figure it out. So how do you do that integration? It's the general. So you have C B 1 minus n, right? Because it's n plus 1, so n is negative, so you put 1 minus n. Does that make sense? And evaluate at V1 and V2. So you'll end up with C V2 minus n minus V1 1 minus n divided by 1 minus n. Now we would like to simplify this. Now, if I have two states, P1 V1 and P2 V2. State 1, pressure is equal to P1, volume is equal to V1. State 2, P is equal to P2, V is equal to V2. Now, what other equation can I write? Now, in earlier case, we have PV equals constant. Now, it's a little different. But, yeah, that's the equation there. But what other equation can we take by looking at those states? If I write the same equation for two states, what I can get? P1 V1 to the power n equals P2, it's a good try. And I can write that also, right? So from that, I'm going to substitute for C, right? For the first term, I'm going to substitute C is equal to P2 V to the power n. And for the second term, I'm going to substitute P1 V1 to the power n. So that's the same, right? If I substitute here for the C, P2 V to the power n times V2 1 minus n, right? Minus, for here, I substitute P1 V1 to the power n 1 minus n, right? So then I can derive P2 V2 minus P1 V1 1 minus n. Now that's the work done during a polytropic process. It's the boundary work done during the polytropic process. Now, can I use this for steam?
Yes.
Yes, I can. Right? Very good. Can I use this for ideal gas? Yes, you can do that. Right? Now, especially for an ideal gas. For an ideal gas. For an ideal gas, I can write, yes, P1, V1 is equal to mR T1, right? And for the state 2, I can write V2 is equal to mR T2. Okay? Now I'm going to substitute those two instead of P2, V2 and P1, V1. If I substitute that, I can obtain W equals mR, right? mR T2 minus T1, 1 minus n. So that equation can only be used for an ideal gas. So these things for an ideal gas, but this equation cannot be used for any substance. Okay? That's the difference. Make sense? Okay. Now, I'm going to show you another couple of relations for a polytropic process. Now, you know that P1 V1 to the power n equals P2 V to the power n for any substance. If process is a polytropic process, for that system, this is true, whatever the substance is. Right? Now, for an ideal gas, I can write those two equations. V1 equals mR T1 and P2 V2 equals mR T2. Now, by using those two equations, I can derive another two equations. Those are V1 V2 equals, so T1 over T2 equals V2 over V1 to the power n minus 1, and I can derive T1 over T2 equals P1 over P2 to the power n minus 1 over n. Right? Try to prove this at home. I have given all the descriptions in my notes, so you can actually follow those, right? And sometimes the equations the numbers might flip over, but the relation stays the same. And in my notes, I have written T2 instead of T1 over T2, I have written T2 over T1, but here V1 over V2, right? The same relation. You can cross multiply and see it. Right? Try to obtain those. And now, you can see that isothermal process of an ideal gas is a special case of polytropic process. When n equals 1, it becomes isothermal process of an ideal gas. But this polytropic process equation can be used for any substance. But PV equals C can only be used for an ideal gas. But sometimes, some problems gives you that, okay, the pressure volume relation is PV equals constant. In that cases, we can use that equation, whatever the substance is, because the problem says that we can use it. Okay, so we have that kind of problem, and we'll go through it, and then you understand. Any questions, guys? Yes? Right here? So it's multiplied, right? When you multiply these bases, what happens to the indexes? Addition, right? Makes sense to everybody? Okay. Good question. Yes?
Last two equations you wrote here, that's just for an ideal gas?
This, yes. This everything for an ideal gas only.
Okay.
But that can be used for any substance. Okay? Write down. Any questions, guys?
Is this volume specific volume?
Well, you can use either because it's a fraction, right? So it's a division. So you can use total volume or specific volume. Doesn't matter. Because the closed system, mass is anyway constant. So specific volume at the state and volume at the state is the same. All right, so let's go through example 3. Example 3 says about a system at a state 1, which is at 1 megapascal pressure, and volume is equal to 0.05 cubic meters. Now that's state 1. And it has a number of subsections, so 4 subsections. So subsection 1, the question asks if the question asks to calculate the work done by the fluid when it expands quasi-statically. Now all the expansions and compressions we consider R quasi-static. Otherwise, we cannot use that equation right here. That is only true for a quasi-static process. Okay. All right. Now, in the first case, it asks if the system undergoes a constant pressure process and end up with this state. Now it's a constant pressure process. P2 is equal to what? 1 megapascal. Very good. And V2 is given 0.2 cubic meters. Right? Now how can I find the boundary work? Boundary work is equal to integration V1 to V2 PdV. Now if you remember the equation for the constant pressure process, doesn't matter, you can use it. So what is the equation that we derive for constant pressure process? Very good. P constant pressure, P naught times, just put V, that's okay, or P1, V2 minus V1. So just plug in numbers and get the answer. Make sense? Right, that's a constant pressure process. Number 2. Number 2 tells me that the pressure-volume relationship is linear. Pressure is linearly reducing. Okay? What do you mean linear? Now, if I have a PV diagram for that process, how can I draw my PV curve? Straight line, inclined into which direction? To the right. So pressure is reducing. Pressure is reducing. Look at the values. It's 1 mega. It's inclined to. Okay. So you have P1 is equal to 1 megapascal, and P2 is equal to 0.2 megapascal, and V1 is equal to 0.05. V2 is equal to again 0.2.
I thought the pressure was 1 megapascal.
Yeah.
Oh, it's in the question. So it's P2 is 0.2 now. P2 here in this case is 0.2. Now this is the second part. And V2 is 0.2 cubic meters. I'm sorry, I couldn't write. I thought that you have read the question. That's okay. Right. So how do I calculate the work?
The area beneath the.
Very good. That's the easiest way of calculating. That's the easiest way of calculating. Now, if I write down this with the symbols, area underneath the curve is equal to boundary work, which is equal to what? How do you find the area of that?
1/2
1/2 time
Poly.
base times
P1 minus P2 and P2 minus
P2 plus P1 times the delta V over 2?
that's right, half times P2 delta V is V2 minus V1. Very good. Now that's the easy way of finding by looking at the diagram, right? By looking at the diagram. Now, I want you guys to go home and do this exercise, and I will give you 20 points extra for the homework if somebody is going to present in the class next time. Of this one, you have to use W 1 to 2 PdV and obtain this equation. To show that area under the curve is equal to the work done, that is obtained by using this equation. Just a hint. How can I represent this line in mathematics?
Slope mx plus b.
Very good.
Change the pressure.
P is equal to mv plus c. Now should be a piece of cake. Right? So you need to obtain, you have to use this integration relation and obtain this work done is equal to whatever we got area under the curve. Does it make sense? The question? Lena?
Question.
Yes.
Why are you adding those two pressures again?
Oh, okay, that's to find the area.
Yeah.
Nothing related to the average pressure or something like that.
No. If you're finding the area, wouldn't it be P1 minus 0.02? I mean 0.2?
No, you have to find the area under the curve to the
The whole thing.
Oh, the whole
X-axis.
thing? Okay. I was thinking of the 0.2 as a,
Yeah, that's
Okay.
the shaded area is the area.
okay.
Right? Make sense to everybody? Right, very good.
So to find the slope line, you just take the difference in pressure over the difference in volume.
Yeah, you can use any technique. I'm trying to see whether somebody can get it. I'm sure that multiple. What?
I work it out a couple points on the test.
Okay. Let's go on. Now, the third one. According to a law, PV constant. Now it says it causes statically expand according to law PV equals constant. Now it has same initial state, state 1, same initial state, P1 is equal to 1 megapascal, V1 is equal to 0.05 cubic meters, and expands according to PV equals constant. Expand according to that law. Right? Now the relation is given. We don't know what is the substance is, but relation is given, so you can use the same equation. So what is the equation for the work done? P1, you can just write the equation. Natural log of HOV. Or if you are given pressures instead of volumes, you can use P1 over V1 instead of these two, as I showed you. But since this relation is given, otherwise we cannot use for anything other than ideal gas. Isotopic process. It doesn't say it's an isotopic process. It just says that it follows that rule. That's it. Okay, next class. Any questions regarding that?
I have a question.
Yes.
You know, future item was, is it saying that the volume is 0.1?
No. V2 is given. V2 is 0.1. This is P1. P1. For the all 4 cases, the initial state is the same. Okay? Initial state is the same. Only the second state change. Number 4. Now number 4, initial state again the same. P1 is equal 1 megapascal. V2 equals V1 equals 0.05 cubic meters, and V2 equals 0.06 cubic meters. And it's expand according to law, PV to the power 3 equals constant. Now what is that process? It's a polytropic process. It's a polytropic process. So when you have a polytropic process, we can use what? W equals P2 V2 minus P1 V1, 1 minus N. We won't be able to use this equation. Why? We don't know that this is an ideal gas. Just say a fluid. Right? It just say a fluid. So now we are given V2 P1 V1, right? We are given V2 P1 V1, but we don't have that. What is N equal? N equals to 3. N equals to 3. Now how do I find P2?
You use
To the power, to the cube equals that. Yes, that's one. Very good. You can use P to the power cube equals P1 V1 to the power cube. Right? So when we get P2 equals P1 times V1 over V2 to the power cube. From that you can get P2, substitute that into the equation and get the answer. Make sense? Right. So that's all the process that we discussed. Okay.